So again we'll be starting with this numerical. Yet here we have to find the reactions as how we had seen in the previous numerical. So again A is hinge and B is roller. This time I have a UVL, that is a uniformly varying load from A to B, and I have this moment as well, a concentrated moment at point A. And then there's something different in this numerical, that is we have this extension of 2 meters and a force of 20 kilonewton inclined at 40 degrees is acting at the end of the extension, right? So again, before finding the reactions, we need to consider the entire system to be under equilibrium, and only then we'll start finding the reactions. So we need to apply the conditions of equilibrium if we consider the entire system to be under equilibrium. The conditions of equilibrium would be the same: summation fx, summation fi, and summation m equals to 0. But before applying them, let us convert this UVL into its point load as how we have done in the previous numerical as well. So converting to point loads, the UVL, as we know, when we convert it into point load, the area of this UVL has to be taken into consideration. So it is, and secondly it's downward, so it would be negative, therefore it's minus half into base into its height, which is 4 kilonewton per meter, which comes out to be minus 12 kilonewton. That is the only force which we need to convert, or only loading which we need to convert to point load. Now we need to do something about this extension also. So to simplify this, what we will do is we will find first the horizontal and vertical component of 20 kilonewton, right? So this horizontal and vertical component of 20 kilonewton, it will act at point D. So the horizontal component will act like this and the vertical component will act like this. Horizontal component will be negative because it is in the left direction. So our sign convention is, if force is towards right, it is positive; if it is to upwards, it is positive, and anti-clockwise movement is positive. So since here it is to the left, it is negative, then 20 sine 40, that will be positive. Okay, so that is this vertical component. Now let us simplify this structure, this extension. What we have to essentially do is, we need to transfer these forces. Basically I need to eliminate this extension and I want to transfer these forces at point C. Okay, now while we transfer the force, this 15.320, first of all this 12.8558, let me transfer that, so it will directly come down. Okay, and whenever we have already learned that whenever we transfer a force from one point to the other, the direct effect of the force is directly transferred, that is, the force itself is directly transferred, but the rotational effect, that also has to be taken into consideration. So what would be the rotational effect due to this force at point C? The rotational effect would be nothing, because the line of action, the C is on the line of action of 12.8558, so rotational effect will be nothing. We can directly transfer this force at point C. What about 15.3209? So again we have a direct transfer of force, but along with that, now this 15.3209 is also causing a anti-clockwise moment of 15.3209 multiplied by 2. So that also has to be taken into consideration, anti-clockwise moment, right? So this is how effectively my structure will look now after that extension is removed from that place. Okay, so now we can draw the free body diagram of this structure. Let me first draw the reactions. VA, HA, then VB is there, right? UVL, which we had converted to point load, let me place it. So 12 kilonewton. We know that when we convert UVL into its point load, it has to be placed on the centroidal location. So this, if this is the 12 kilonewton, the centroid of the triangle is basically base by 3. So base is 6 meters, 6 by 3 is 2 meters, and that 2 meters is measured from the right angle of the triangle. Right angle of the triangle. So this is nothing but 6 by 3. So this 12 kilonewton is acting at 2 meters of distance. After 12 kilonewton we have 10 kilonewton, which is acting like if this is 1.5, right? So this total is 6 minus 1.5, which is 4.5 meters, and out of 4.5, if this is acting at 2 meters, therefore the remaining will be 2.5. Then we have VB, which is at 1.5 from 10. Then we have all these three forces. So this is our free body diagram. After drawing the free body diagram, we just have to now apply the conditions of equilibrium, starting with summation Fx equals to 0. So summation Fx equals to 0, this HA is acting in the positive x-axis, so it is plus HA, and then we have this horizontal force, which is minus 15.3209, so HA comes out to be 15.3209 kilonewtons. Then summation Fy equals to 0, we have VA is acting upwards plus VB also acting upwards, minus 12 minus 10 plus 12.8558, right? This has to be equal to 0. So we get VA, this entire thing comes out to be VA plus VB is 9.1442. Then we need to apply summation of moment at a point to be equal to 0. Generally you can apply at any point, but you need to select the point such that your maximum number of forces get eliminated. So A is the point where we can apply the moment, summation of moment to be equal to 0. Summation MA equals to 0. VB into, okay, we'll start from this this moment itself, minus 10, because it is clockwise. And now see, this moment, even though if it is acting at point A, the moment should always be considered no matter at what point it is acting. If there is a concentrated moment in your structure, definitely that concentrated moment will come in the moment equation, no matter if it is acting on the point where we are taking the moment or if it is acting at any other point, still it has to be considered. So this is minus 10. Then we have 12 into 2, again it is clockwise, so it's minus 12 into 2. Then 10 into 4.5, which is again clockwise, so it's minus 10 into 4.5, plus VB into 6. Then this is an anti-clockwise moment, so it's positive plus 30.6418, and then due to this there won't be any moment, but due to 12.8558 again there will be a anti-clockwise moment at point A. So that is, I think, 12.8558 into 8 equals to 0. Here the only unknown is VB. VB we can find out by solving this equation. VB will come out to be minus 9.08137 kilonewtons. Now you see that now we are getting VB as negative. It means that the direction that we had assumed of VB, the direction, upward direction, that is incorrect. The true direction or the correct direction of VB is downwards. Okay, so what you can do is that you can either show your downwards and write VB as positive, or you can leave it to be upwards in this free body diagram and you can take the value to be negative. Okay, either of them is fine. VA plus VB is 9.1442. Now remember, this equation of VA plus VB we had found when we had assumed VB to be upwards. And when VB we are assuming upwards, its value has to be taken as it is what we have found here, that is negative. So VB I will have to put here as minus 9.08137, which when it will go to this side it will become plus. So VA you will get as 18.2256 kilonewtons. Now let us understand why we got VB as a downward reaction. Okay, we got VB as a downward reaction. Let us understand why. So it is predominantly because of this moment and due to this force. See, this moment is a very high moment. It is 30.6418 kilonewton meter, and again 12.858 kilonewton multiplied by 2. You see that both of them are trying to cause a moment anti-clockwise, or both of them are trying to take this part of the beam upwards like this. So this point B is actually trying to go upwards, and this roller support is trying to pull it downwards. That is the reason it is giving it a downward reaction. Because point B tries to go up, your support will not allow it to go up because there is no movement. It is not allowing movement in the vertical direction. Hence, it has to pull it down. Therefore, there is a reaction which is downwards. Now let us solve this numerical. This is a propped cantilever. If you see, the end A is fixed and the other end is a roller support. So it's a propped cantilever and it has an internal hinge at point C. Now let us see how to solve such structures which have internal hinge in them. We again need to determine the reaction at A and B. A is fixed, so it will be developing 3 reactions: vertical, horizontal and a moment. At point B, we have a roller support, so it will be developing 1 reaction, normal to the roller, that is a vertical reaction. Now we need to first convert all these varying loads into their respective point loads before solving. And you see this UDL here, it is actually inclined UDL, and it is inclined at an angle of 30 degrees, right? So first let us convert the point loads, convert these varying loads. Now I will consider this uniformly varying load from A to C complete. I won't consider it as 2 right angle varying load. You can do that also, there is no problem in that. You will get the same result at the end. So if I convert this UVL from A to C, it will be minus half into base is 5 into height is 4, so it's minus 10 and negative because it is acting downwards. Then we have this UDL, which this UDL we have to now convert it into its 2 components. The horizontal component of this UDL from D to B will be, now see, the thing is that you just have to take the area of this rectangle 2 into 5, okay, 2 into 5, and then the cosine component will be vertical since this is the angle, and the sine component will be horizontal, right? So you just have to multiply it by its sine component and cosine component, like how we do with the normal loads. So it's minus 2 into 5 sine 30, so it's minus 5 kilonewtons, and the vertical component of this will be minus 2 5 cos 30, it's minus 8.6603 kilonewtons, right? Let us now draw the FBD of this. So here we have these 3 reactions and the 4th reaction at point B. This 10 kilonewton will be, now since this load is a symmetric triangle, and as I told you that the centroid of a symmetric triangle will always lie on the axis of its symmetry. So this is the axis of symmetry and the centroid will lie exactly at this point. So it is 5 by 2, which is 2.5. Then we have this 10 kilonewton load at point C. We have these 2 components at a distance of 1 meter because 2 by 2, or the centroid of our UDL is basically half, right? So it will be acting at 1 meter. The structures with internal hinges need to be separated at internal hinge, and each segment needs to be analyzed individually. This is how we generally solve when there is an internal hinge. We will separate the structure at the internal hinge. Now the question is, where will this 10 kilonewton go if I separate it? So the thing is that you can take it, you can keep this 10 kilonewton either on this right side structure, or you can either keep it to the left side structure. My suggestion always is that you should keep it to the structure which you will be analyzing later on, or the structure which you will be analyzing last. So the procedure of internal hinges, when we separate it, you will be getting 2 structures, first and second structure. Whichever is the easiest one, that you will be solving first, okay? So my suggestion is that this 10 kilonewton should always go on that structure which is analyzed the last. Let us separate it. So when we separate at internal hinge, we know that at internal hinge we have two reactions that are formed because it cannot resist moment, thus only two reactions it can give, VC and HC. So this VC and HC, here you can see this VC is upwards here and this HC is this way. Same way, when I transfer it to this segment, I'll call it as first segment and this is second segment. When I transfer this HC and VC to this first segment, their directions will be reversed. But I am not showing here now because I do not know exactly whether VC is having a vertical direction or whether HC is having this direction or not. This we will get when we analyze this second segment. And why am I analyzing this second segment? Because it is easier to analyze this second segment. Okay, that is the only reason I am doing it. So HC and VC, and we have these loadings here. What we can do is we can apply the summation of fx, fy and summation m equals to 0 on this segment and find HC and VC. The net horizontal force, and that is equals to 0, which is summation fx equals to 0. What I'll get is HC is equal to 5 kilonewton. So I found HC directly. Then summation Fy equals to 0, that is I'll get Vc plus Vb equals to 8.6603 kilonewton. Okay, so this is one equation that I'm getting. The second equation, summation m equals to 0, so we'll take summation of m at c equals to 0 such that Vc and Hc both will go, and even this 5 kilonewton won't have any effect. So Vb, okay, 8.6603 into 4, which will be clockwise, and then plus Vb into 5 equals to 0. So I'll get Vb from this, right? So Vb is 6.92824 kilonewton. After I get Vb, I can find Vc. So Vc is 1.73206 kilonewtons. What we see here is that we have got all the values to be positive. It means that the directions that we had assumed are correct. So the direction of HC and VC is correct in this point, right? So I got HC, I got VC, I got VB. As I told you that these reactions, when I want to analyze my segment 1, these reactions what we have found here, HC and VC, they need to be transferred to your segment 1. And when we transfer them, you need to change the direction of those reactions. So this VC which was vertical here, it becomes downwards, and this HC which was to the right, it becomes to the left. Okay, now we can analyze this segment 1. See, the reason that we did not choose segment 1 before to analyze is because if this was not known and if this was not known, VC is not known, HC is not known, HA, VA and MA is also not known. So how many unknowns would have been there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 unknowns would have been there. 5 unknowns and just 3 conditions of equilibrium, we could not have solved it, right? That is the reason compulsorily we had to take segment 2 to solve first. Okay, but now I know my HC and VC, so the number of unknowns are only 3 and this can be solved easily. So let us apply summation fx equals to 0. What I'll get? I'll get HA is equal to 5. HA is equal to 5 kilonewton. So I got HA also. Now VA, when we apply summation Fy equals to 0, what I'll get, the equation will be VA minus 10 minus 10 minus 1.73206 is equal to 0. This is the equation that I'll get, right? So VA I get directly from here. VA will be 21.7321 kilonewtons. And now the only thing left is to find this summation of MA equals this moment at point A. So what we'll do summation of moment at point A to be equal to 0. Net moment is 0. So HA and VA will go, they won't have any contribution. So we have this 10 minus 10 into 2.5 because it is clockwise, then minus 10 into 5 and minus 1.73206 into 5, right? And then we also have this MA which is acting at that point. So MA at point A, it will be taken into consideration. Minus 10 into 2.5 minus 10 into 5 minus 1.73206 into 5 is equal to 0. We can find MA from here. MA comes out to be 83.6603 kilonewton meter, right? So we have found HA, VA, MA, VB, everything we have found, right? This completes the numerical, and that's it for this lecture. Till then, take care. Thank you.